Hello.
Hello.
Hello, everyone. Welcome.
Yeah.
ITS 350. All right, so I'm just going to let everyone in. Okay. All right, so you should be seeing the whiteboard at this time, right? And
That is correct.
great. So this is ITS 350. All right, and today's a lecture. So we are going to just continue our discussion pretty much where we left off. Last week, we were looking at block ciphers, basically secret key encryption. You started working on your first lab. So I'm just letting some people in. All right, so secret key encryption, and you started your first lab. You had some problems there to solve. Remember, that lab is due this Thursday by 10 p.m. And I believe I've created the Dropbox for it on Brightspace, right? So some of you have submitted already?
Yeah, it's there.
Okay, great. All right, so that's done then. And then this week we have a new lab. It's going to be related to the principle of integrity. And so that basically means hash functions. Which is another one of the primitives of information assurance. Okay, and so we are going to look at this just to give you an example. You know, primitives like hash functions were used to create things like blockchain and Bitcoin and all that. Now we're not going to cover that in this class. You know, that's a topic in of itself. But I believe in our program we do have an elective course about cryptography and about the blockchain and Bitcoin, and that's taught by Professor Xiangping Wang. So you can email him about when the course is offered. But anyway, for us, you know, my point here is that hash functions are primitive in cryptography. And then you use these in combination with other things to build much more complex systems. All right. So there's also, if you have the Seed Labs book by Wenliang Du, he's got, in the integrity chapter, he actually does cover a little bit of Bitcoin, I believe. Yeah, blockchain and Bitcoin. So that's chapter 22. So for those of you that like reading along, I would recommend you read for this week for integrity and hash functions. You might want to read chapter 22, and that's called a one-way hash function. Although I'll explain a lot of this in the class. Okay, so one-way hash function. All right, that's the title of it. And also remember, I do have slides posted. So a lot of these topics are summarized in the slides. You can also read the book, but I'll just write on the whiteboard today, kind of go over some of these concepts. But that would, chapter 22 would correspond. It's the chapter that's most aligned with the lab that we're doing this week, okay? Which is the integrity lab. This lab is actually, we're only going to do the first 3 problems, so it's a little bit kind of a simple lab. And so what I do in this week is we do the first 3 problems, and then you have your first script. So I'm going to do a review of Python, just a very short, quick review of Python, and then we're gonna look at a substitution cipher. Okay, just to kind of get warmed up with the cryptographic algorithms, just so that we can, see how things work. So I'll give you a little bit of, a little bit of code on that one, and then I'll just leave some parts for you to figure out. So the lab this week will be like this. All right, so it'll cover that. So if you want to learn a little bit more about, read a little bit more about substitution ciphers, although it's not the exact same program as the one in the book, and you want to learn about the Enigma machine and all of that fun things. Chapter 21, which is secret key encryption, pages, basically from the introduction, substitution cipher, monoalphabetic substitution cipher, breaking monoalphabetic substitution cipher. You can read through all of that up until the Enigma machine, basically. And that should be a fun read. But as I said, I will provide also my own script, a different kind of script, just for us to practice. All right. Okay, so that's the plan. And the description of the problem will be provided in a Word document. Okay, so that being said, so that's kind of the plan for this week. Okay, and then today, I'm just going to finish up what our discussion from last week of the OTP. So I'm going to pick up where I left off, go over that, finish it, and then we're going to get into message integrity. Message integrity. All right, so as far as the Python scripts, so I would recommend that we just do them on the VM, on the seed VM. So usually what I will do probably is I will use the seed VM whenever. I'll show you guys how to write them there. However, some of you, if you have Windows operating system and you want to do it that way, just install any editor that you feel comfortable with. Jupyter Notebook or Anaconda environment, or one of those. But you will see me mainly do these on the CVM, given that most of the labs we do in this class are on the CVM anyway. Okay. I did provide on if you go to, well, I'll do a very quick overview of Python. I did provide, you guys should be seeing the Brightspace environment now. If you go to resources for ITS 350 resources, you will see something called the lab background files Python. So I would recommend, if you can, print this out, or and just read through it. Certainly practice it. It's got some examples of Python. And then, as I said, I will do a few examples of simple things. Yeah, all right. Okay, so now let me go back to the whiteboard. So before I begin with our discussion today, are there any questions?
Not that I can think of.
Nope. All right, great. Excellent. So let's go ahead and start. So if you remember, we were talking about cryptography, right? And we looked at XOR operations. And we said that we want the encryption to be fast, so XOR certainly is the fastest. We looked at how XOR has a specific operation, right? We talked about that, how you do things. And then we started to talk about, so what is a secure cipher? So that was really where we left off. What is a secure cipher? Right, so that's the very first thing that we need to address even before we determine, okay, yeah, this works really well. So you can't, you know, obviously through experiment, through the fact that every year, you know, thousands of people try to break all these encryption algorithms, you know, we also want to, besides experimentally and just trying things out, you want to have some theoretical framework. All right, so we talked about how the OTP basically says that you have a message M, and the definition is that you basically just apply an XOR operation, but you need the key to be as long as the original message, right? So that was the definition of that. So then the question is, how do we, what makes a cipher secure? Okay. And so the idea was, as we stated, was that the ciphertext should reveal no information about the plain text message. Okay, and then Claude Shannon, basically, we talked about Claude Shannon and other people in the field, somewhere in between the 50s and the 60s, they came up with, let's just say Shannon. Came up with an idea, basically, or a definition of what makes a secure cipher. So we can state simply, without getting into too much detail, just the main idea of this, that a cipher, which will have an encryption and a decryption algorithm associated over a space of, let's say, all possible keys, all possible messages, and all possible ciphers, right? Those are all the elements involved in this encryption. And an XOR operation, and that pretty much defines the entire system. For messages of equal length, for instance, we have the following rule, right? So we have a probability, or we want two probabilities to be exactly the same. No one of these bigger or smaller than the other. All right, and so this is what would define a perfect algorithm, that we have an encryption given the same key and a message 0 that produces a cipher, and another encryption of the same key but given a different message M1 that produces a cipher, right? So that's basically the definition that we have under which we can define, you know, what is a secure cipher, right? And we had said, you know, all these are the, as I said, the key space, the message plain text space, the cipher space, all right? And so what we want is, whenever we create an algorithm or a cipher, we want it to meet this condition, all right? And we had said already last week, and that's where we kind of stayed, that if we intercept the cipher, right? If we intercept the cipher, which is the only thing that the person that's trying to intercept it should get access to, and they know the encryption algorithm, they definitely don't have the key And so basically, given the cipher should give us no information about M0 or M1. And so another way of saying this is, given the cipher, there's no way that we can know that, oh, this is more likely to have come from M0 than from M1. We can't even know that. It has the same probability that this cipher could have been generated from M0 or M1 or any Mn for that matter. Okay, but this is just a way of stating it. So I'm going to put it in word, and so this is where I'm going to continue now. So that means, oops, that means basically that given the cipher text, you cannot tell if the message is M0 or M1. So you just don't know, right? Because they have an equal probability. And while that seems like not very, profound, it is actually very useful. Okay, very useful. Another way of saying this is that the probability is the same So if you are an attacker and you intercept a particular ciphertext C, which is what I was saying, so remember you have Bob and Alice, right? And there's a firewall here. There's a firewall here. And the keys are hidden behind the firewall, but the cipher is sent over the internet, over an unsecured channel. So Zelda can intercept. So the probability is the same. So if you are an attacker and you intercept a particular ciphertext, then in reality, the probability that the decryption of C is M0 is exactly the same as the probability that the decryption will give you M1. So we want to say the probability that the decryption of C is M0 is exactly the same as the probability that the decryption will give you M1. So another way of viewing this is that there's no, so if you are a hacker, right, and maybe you can't break it immediately, but if you could, from the cipher, say, okay, I think, I see this pattern of S's, and I think this thing has more S's, so it probably came from M0. Even if you just had a little slightly more information, given the cipher that you could tell, oh yeah, it's more likely to have come from M0 than from M1, then that would be a bad cipher. It's got to be something where you have the cipher and you look at M0 and M1 and they're equally likely. And that's pretty much like think of it as flipping a coin, right? It's sort of a random thing. So it's supposed to be a random as much as possible. That's the key insight with this idea. So if all you have is the ciphertext, which is what you intercept over here, because Zelda can only intercept the ciphertext. Now, if Zelda breaks into the firewall and steals the key, that's a totally different story, right? The scenario assumes this only, okay? So in that case, so if all you have is the ciphertext, then you have no idea whether the ciphertext came from M0 or M1. Okay, and that's really the important idea there. All right. So does that make sense, guys? Is this
Yeah, that makes sense.
okay? All right, great. So that's, you know, that's the definition. I usually try to write it out, you know, so that semantically we can, in words, basically, we can interpret this. All right, great. Sounds like everyone gets it. That's good. And that's it. That's how you define ciphertext, right? So if you ever have an algorithm, you know, and you think, let's say you created your own algorithm, right? You spend a lot of time, many years doing research, you come up with your own algorithm. Well, you're not just going to say, okay, use it. And, you know, and let's see if anyone breaks it. Obviously, that's part of it. People will try to break it. But also theoretically, you start with that. You start and you try to measure somehow, okay, how likely is somebody to infer something from the cipher? Now Shannon, as he was working on all of this, going back to the OTP, given that definition, you know, remember that the OTP has this idea, right? Have the message, and then you have the key. Just gonna mute you guys. All right. So you have the message and the key. Now we've learned that with block ciphers, we have to use the same key, break it into blocks, and that's in a sense the problem, right? Because we're repeating the same key, and that's why there's several modes of operation. As you have seen, though, when you have a smaller key and you're repeating it, a pattern might start to emerge. That was actually the goal of last week's lab, and hopefully some of you have already solved that. However, in the OTP, as Shannon describes in his discussion, the key has the same length, and the key should be as random as possible, right? So what is called pseudo-random. Should be pseudo-random. So Shannon basically proved that to have perfect secrecy, so Shannon proved that to have perfect secrecy, the length of the key length, right? The key length would have to be greater than or equal to the length of the message. Now, keep in mind, that's to have perfect secrecy, okay? So, just use a different, perfect secrecy. All right, so you have to have, now, practically speaking, you don't always need perfect secrecy. Sometimes good enough is, well, good enough. And so Shannon did prove, and it's intuitive actually, right? Because as we have seen with the ECB, for instance, which ECB is at least the less secure, we take the same key and we just repeat it. But when we perform an XOR operation, and these are A's, and this is the same sequence of bits, they're going to be the same. So these cipher 1, cipher 2 are going to be equal. And so there is, therefore, a pattern which makes it not really as close to pseudo-random as we want it to be. Therefore, we can see the problem. However, if we have a key, as long as the message itself, you know, it's not repeating because the key itself is pseudo-random, right? And so, therefore, according to Shannon, he proved that it would have perfect secrecy if it met all of these conditions. But unfortunately, it has to be greater than or equal to the message. And the problem with that is that that is not efficient. So the rule of length of key being greater than or equal to length of message, plain text message, is not efficient. So this is not efficient because imagine the scenario of Netflix. You want to watch a movie. Let's say you just downloaded, you know, or a series, right? You know, 10 episodes or 8 episodes of some show. That's 8 hours or 40 minutes times 8 of content. Certainly that's going to be a lot. Imagine now you have to, for that to be sent securely over the internet so that people don't just download the movies for free, they would have to, you have to encrypt it, and then you would have to send a key as long as the movie itself. And so that, you know, sending that key would take a lot of work. So it's not practical, unfortunately. Okay. You know, imagine the entire Encyclopedia Britannica, right? Or all the or the equivalent of that today, which is the whole of Wikipedia. So that would be a lot to deal with. All right, so given that we established that using a key is, so we've established that using a key, as long as the message is, if you want to call it, it would be theoretically speaking the gold standard, but it is not efficient. This is not practical. Think about the fact that also you have, you know, computers, CPUs that are 24, you know, 32-bit, 64-bit, and they perform operations on these. Imagine if, and the advantage of XOR is that you can give it the key of a specific size and it does the operation in one XOR in parallel. But if now you're giving it a gigantic movie or a gigantic, I'm trying to think what's the biggest multimedia, you know, just something, right? I mean, I think a movie is the biggest.
Blu-ray is like 30 gigs.
Yeah. And so you give all of that, the computer will not be able to perform all of that in one single XOR operation because, you know, it doesn't have anything as big. So it'll have to break it up. And it just becomes impractical. Okay. So that kind of lays then, lays for us, given this idea, okay, we can't use keys. We have a message, obviously. And then we have a key, but the key cannot be as long as the message because it's impractical. Therefore, we end up with systems where the length of the key is actually a lot smaller than the message. And that leads us to the idea of block ciphers or symmetric ciphers. And of these, you know, we will, as we advance, look at these two, DES and AES, so the data encryption standard and the advanced encryption standard. We'll talk about these later on. So I'll discuss the algorithm for this one, and it'll become really obvious, really, how that works. And you'll see it's just block, you know, breaking up in blocks and XORing and all of that good stuff. So that's what you've been exploring. Hopefully all of this makes sense. That's what you've been exploring this, this week with the labs, okay? And so usually what I do here, instead of diving into DES and AES, because this can take some time, I like to introduce other primitives so that we, you know, because by having, so if I only focus on DES and AES, I'm gonna be missing other primitives. I'm gonna introduce them later on. And then when we try to make more complicated systems, you know, we just won't be ready. So instead, I will come back to DES and AES to look at the algorithms themselves in more detail in maybe a couple of weeks. And now, but you understand how block ciphers work now, just, you know, divide this. And so now we're gonna move to another principle, which also uses block ciphers, I should say. I mean, it uses the same mechanisms and it uses XOR. It's just now we've been focusing so far on secrecy, right? Which means we've been focusing on what pillar? In all of what we've been doing with encryption and decryption, which pillar have we been focusing on so far?
Confidentiality.
Confidentiality, exactly, very good. Right, so we've been focusing on confidentiality. Now we're going to move on to another pillar, integrity, all right? Now, who can tell me, what was the definition of integrity? What does that pillar address?
Basically that the document hasn't been, or document or whatever data hasn't been modified maliciously or from what it was originally supposed to be.
Perfect, exactly. So in this scenario, again, we have Bob and Alice. And we have a channel. We have our firewall over here. Firewall, and then this is the internet somewhere. The web. All right, and so again, we're gonna send a message. Now, keep in mind, this message doesn't necessarily have to be encrypted. So here we can send a message or a cipher. It really doesn't matter because we don't care about confidentiality. You see, so if I cared about confidentiality, then I would send a cipher. But because we're only really, let's say, concerned about, and there are some legitimate situations where you're only concerned about integrity, right? And so in that case, we can actually send only the message, right? But the message has to be accompanied by something, let's just say something, that helps us to determine integrity. So what's one example of something that you can send over the internet where you only care about integrity but not confidentiality? What would be one? What examples can you guys think of about that?
Video streaming, maybe?
Say that again?
Video streaming, maybe?
Like what kind of video streaming?
Like live streaming or something like that, like on Twitch or something?
On Twitch, right. So, yeah. So if you, yeah, okay. What else? See, somebody wrote something here. Okay, sure, memes, something funny, right? That doesn't necessarily have to be a secret. What else? So one example could be, and this is just one of others, it's like things that are already free and available. Like you have a computer program, for instance, or you have software on GitHub, right? So the software is there, it's free to use. There's no need to encrypt it if it's already public, but at the same time, the creator provides some kind of a something that helps us to determine that when I downloaded that file, it hasn't been modified. Okay? So as you might imagine, that's what we will be doing in the lab this week. Just like you did last week with ghex, you're going to be sending messages, whether encrypted or not, and you're going to check, right, that you send them from here and that they check out on the other end with integrity. You're also going to take a message and you're going to flip one bit. Just one out of millions. And then you're going to recalculate for integrity to try to determine what happens to the integrity of the message. Can you tell if it was modified, even if it was just one simple bit? Okay. So let's get started with that. Okay. So let's talk now more formally about message integrity. Now there are some times, and this is where now we will start to connect the primitives where we want both confidentiality and integrity. So in that case, if I ever gave you a problem like that, then you both have to encrypt the message and then check integrity, and you have to prove to me that the way that you did it, meets those conditions, right? So a lot of what we'll be doing, especially when we start doing our practical exam, will be that you have to do those problems, right? So I'm going to ask you in a problem, okay, take this message, send it, and achieve confidentiality, integrity, authentication, and so on. So we'll be combining primitives. But for now, let's just define message integrity. So, as you guys have all stated, let's formally say, make sure the files have not been changed. Not been changed. And so you want to make sure the files or the file in question has not been changed. And usually this thing that I had mentioned as a question mark is actually called a MAC. You'll hear me call it the hash sometimes. But basically the idea is that you have a message authentication code. So that's some of the terminology. So graphically, we have, again, Alice, Bob and Alice, right? And they want to communicate securely. Now there's a key of some type associated with this, right? And then you send the message So you send the message, and along with the message, let me say the message M. And along with the message, you're going to send a little tag. Okay? The tag is nothing more than a sequence of bits, right? So, 128 bits, whatever. Right? We'll see in a second an algorithm, a very simple algorithm that will give us an idea of how this works. Of course, with the lab, you're gonna still be using OpenSSL, just to run the commands there as we did before. Okay. So then, you know, when Alice, who's sending the message, will use a MAC, what is called a MAC signing algorithm. So let's define for integrity, right? We're gonna basically define an algorithm of some kind of function S, you know, for signing. And so the function could take a key, the message, and its output is going to be this tag, right? So it produces this tag, which is the thing. Then now when you transmit the information over the channel, you have the message and you have the tag as a pair. So it goes from Alice to Bob. So when Bob receives it, Bob will, you know, use the same function to try to prove it came, you know, it is in fact the same value. So whereas Alice uses the signing algorithm, so Alice uses S, then Bob will use a function V, you know, to verify. So Bob uses a verification algorithm. And usually with these functions, instead of when you do the verification, it really just returns true or false. It doesn't return, you know, there's no point in returning the message again. You know, you're not decrypting. In fact, you might have the message. So instead, what you do is some kind of a check of the values, and you then, you know, provide V given the K, the M that you received, the tag, right, which is that tag, okay? And then this should return true or false. So that's the general idea there, is to do that. Okay, so that's you know, this one's pretty simple to understand actually. So the implementation of this kind of technique is to use our basic, you know, so how, you know, the idea is how do we build one of these? How do we build this signing and verification functions to obtain integrity? So how do we do it? So we can use the, you know, the basic building blocks that we've seen so far. So how do we create these algorithms? All right, so that's the question. So we can, there's, you know, hash functions. All right, or we can actually, the approach we're going to take mainly here is to do a block cipher algorithm. Right, so we can take that. I'll define hash functions in a second, but I may not get into the details of them until later. But for now, given that we've been talking about block ciphers, we're going to consider a simple approach to create these hashes. All right, so I talked about these approaches, you know, some hash algorithms of any kind, or using a block cipher to create the hash. So let's first of all, define what a hash is. So that's probably a good place to start. So what is a hash function, let's say? So cryptographic hash functions. All right, so we're going to define that. All right, and so how can we define this? So simply we can say cryptographic, a hash function, let's say, a hash function. Oops. A hash function, okay, is an algorithm code as an algorithm, and here's the trick. This is it, right? We just need some algorithm that maps in some way, right? And usually functions are that, right? A function takes an input, gives an output. So in between, there's some kind of a mapping mechanism. So a hash function is an algorithm that maps data of variable length to data of a fixed length. Okay, and that's it. Notice what that means and what that implies, right? So we're saying that we can have, a message that continues down here and down here that is that big. It goes through some hash function, and that hash function always produces something of fixed length. So whereas this is variable length, this one over here is fixed length. So let's just say, for the sake of argument, this is 256, oops, or 128 bytes or whatever, right, of information. Remember, it's all zeros and ones, right, ultimately. But let's say, 1 byte has 8 bits, of course, so then 128 of those. And that's your hash value. You just determined that that's going to be your hash. All right, and then this is anything. So for instance, this could be your VM, your entire, 20 gig VM or whatever, or a file, any file in the file system, files. Right, and all of these then, you need to convert this of variable length into a hash of fixed length. And so that's the definition of this. So hashes have a lot of uses, actually. Hashes, they meet some conditions. One of them is that the hashes need to be unique. That is to say, if you have two messages that are almost exactly the same, right? This one just has, 1 bit out of thousands, 1 bit out of millions, let's say. That's different. Even if that's the case, when you run these through the hash function, the output of it, which is a fixed length hash, will be totally different. Totally different. Okay? So that's an important point. Not just like slightly different, but totally different. That would be the definition of a really good hash. Okay? So if you ever have a situation where two different messages generated the same hash, you have what is called a collision. And so theoretically, it's possible, but it shouldn't really happen with a good algorithm. So an example of hashes are used for a lot of things. So for instance, they are used in malware detection. Anyone know how hashes are used for malware detection?
Can't the hash of the actual virus be recorded and then added to some kind of blacklist for any antivirus software or whatnot?
Yeah, exactly. So what you would have to do is you have all the files of known viruses, you calculate their hash, then you have a database. Then whenever you scan your system, you check all the files, convert them to a hash, and then you compare the hashes. Any hash that matches your database should be a virus, right? Now, what's one way that a virus can evade this mechanism?
If its hash constantly changes?
But how? How do you constantly change the hash?
By constantly modifying itself, I would guess.
Yeah, yeah. And how much does it need to modify itself every iteration?
A single bit.
A single bit. Perfect. Exactly. Very good. So that's exactly what I was saying is, you know, it's so easy. And that is what is called a polymorphic virus. Okay. So I want you guys to understand that a polymorphic virus is basically a virus that does that, because the antivirus works on hashes and things like that. So then, hey, I'm just gonna, every time I make a copy of myself, I'm just gonna create a new random number there somewhere in the code, and that will generate an entirely new hash, and boom, I evaded the antivirus. All right, so that's one of, actually later in the semester, we will look at we'll write some code in Python, and we will mimic that. We will create a self-replicating virus that's polymorphic without a payload. But the principle is pretty much this, you know, we've already stated it. We just have to change one bit in the file, and that's it. So for malware, sometimes people use hashes for looking up files, right? So if you have several files in the system, you know, file 1, file 2, file 3, and so on. You save the path, and then, you know, you always can just look up something about the file by the hashes. So that's more for referencing things. So it has applications in that field. We're not going to look at that field, but just, you know, be aware that that's something else. All right, so we've talked about hashes, and we've provided now a formal definition of them, right? So this is the formal definition. This is the formal definition of a cryptographic hash function. So now let's move on and try to write the pseudocode, or the main algorithm, for a very simple hash function. So very simple, but it should provide, you know, some more intuition. So let's call this, and feel free to implement this in any programming language that you like. It's not going to be homework, but it's something that you can, at least I don't believe it's part of the homework, but it's something you can try on your own. Are there any questions so far, guys?
I don't think so.
All right, great. So let's look at an example here. Let's look at an example. Let's call this a very simple hash function. Right? So a very simple hash function, and it's going to be built on top of XOR. So you can see how important XOR is for a lot of things. And again, it's because it's fast. In one of the labs in a couple of weeks, we'll see that we'll focus on performance, and you will see that some algorithms are faster than others. And so you'll see why whenever you create a cryptographic algorithm, you must always consider both the security of it, but also the performance of it. So so what do we need? We need some assumptions. We need an algorithm. We need an algorithm, right? To compute the hash code of a message. Okay, so that's that's the goal. Plain text message. To simplify this, we can view let's say we can break the message into a sequence of n-bit blocks. So we can break the message into a sequence of n-bit blocks. So you can see once again, we might start with a message that looks like this. We're going to write our code. You know, it's like, you know, when you treat it as, you know, like you do programming, right, as an array, and just kind of slice out the individual segments. So we're going to take, you know, this segment, then that segment, and that segment, and that segment, and that segment. And if you think about it, we just need to go from whatever the length is of this message, which is variable length, into fixed length, which could possibly be just the size of the block itself, right? So our hash length could be, so the hash length could be equal to the block size, for instance, right? So that, you know, this is an algorithm, so we're just defining it. We're defining the ideas that we need, and then we're making some assumptions later. So how big or how small you make that block will depend on performance and also how secure it seems to be, and so on. Remember that usually you'll have a key associated with this for additional security. And the key, to keep things simple, could also be the same size as the blocks themselves. Let's say this is block 1, block 2, block 3, ... block n. Now, what would happen if, I need to redraw it. What would happen if I have this situation? What would you guys suggest? Adding padding, exactly. So in that case, padding would be the approach, which, as you can see, is pretty much what we've been doing so far, right? Block cipher. So we can just add padding if necessary, and that gives us the algorithm. But here we define our basic structure for a very, very, very simple XOR algorithm. Okay, so we've said that all algorithms for computing the hash code of a message view the message as a sequence of n-bit blocks. So we did, and I should have said, this is n bits, just so it's better defined. So it's n bits, however many bits you want it to be, maybe 128 bytes, and then 128 times 8 times 8. That's going to give you the number of bits. All right. So we've defined that. And then we also define, so once we have blocks of size n bits, right? Then we can proceed to the next one, which is how to process the message. So the message is processed one block at a time. One block at a time. Right? So we do one block at a time there in some kind of, iterative, in an iterative fashion. Right? So a loop of some kind, and that will produce a final and a hash. This produces a hash of size in bits, which is the same size as the previous one. So notice they're the same size. So in summary now, we have the algorithm, and we can state it as, start with the first n-bit block, right? So we start with that, XOR it with a key or another block. Another block. Then XOR this result with the next block. And so on. Right? And so that would be in words, basically, the way that we can proceed. And so we can call this an XOR hash algorithm. So this would be an XOR hash algorithm. Another way now, more programmatically speaking, we're going to say we have a list of blocks, right? List of blocks. And then we have the, let's say, and then list of blocks, and then we say split message, right? In blocks of, let's say, 128 bytes, right? So that gives us a list of all the blocks, right? I'm going to assume for this one that, well, actually, let's just do 4 block in list of blocks, right? And if I do that now, what am I doing? in this. I'm iterating through the list of blocks where now I took the message, split it into blocks of 128. This function split would be a good place to do the padding, okay? So if you know, so I'm just for completion, so to make it obvious, I'm gonna say, comma, padding equal true. And what that means is that, you know, inside the split function, I'm always gonna check the size of the block, right? And if one block is less than 128, I'm gonna pad it. So now this assumes that all the blocks have been padded, right? And so now what I can do is temp block or temp cipher, whatever you want to call it, and it's just going to be block. And actually, I'm going to imagine I have a function called XOR. So I'm just going to call the function XOR, and I'm going to take block. And what do I XOR it with here, do you think, guys?
The key or another block.
Perfect, very good. So what I can do is I'm just going to initialize temp block to, for instance, the key. That's a good one. All right, so you can see now then I just do temp block, right? And so what's going to happen is every iteration now I take a new block, right? So I take, you know, I have the key in the temp block, so that's going to be in here the first iteration there. And then I take the current block, the first block, XOR them, that gives me temp block. Next iteration, now I have the, you know, the result, which was block, and the key, that's in temp block, and then I take the next block, XOR it. Great, I do the third iteration, take the next block with the result of the previous one, and as you can see, I'm XORing everything in this loop, and at the end of the day, I got the whole message XORed plus the key, so everything is pretty good. And then at the end, I'm done. You know, once I've XORed everything, and then I'm just going to say something like return temp block, and that's going to be my hash value, basically. Assuming, you know, this is a function, of course, and the function then for its usage, I'm just going to say down here, you know, I'm going to say hash. So imagine now this is outside the function call, right? And so this function call would need what? Let's say simple, let's call it simple hash function, right? And then this needed to take, what arguments does this function need to take? We know it returns the hash, right? What do you have to give it?
The block.
Which block?
The message.
The message, right? That's what you do, because the blocks are broken inside, so you just provide the message. Oops. You provide the message. What else? So maybe if I do this, so I'm going to define it, function, simple. You guys can see what I'm writing here, right? The function.
Yeah. So is the stuff above the line the simple hash function that you're?
Yeah. So the
Okay.
definition of the code is this, and then what I have under the line is in some other program. I'm just calling this function.
Gotcha. So you would be passing it. We'll need a message and the key.
There you go. That's it. You see that? So we've defined a very, and that's it. That's how these algorithms work, right? So this is what, you know, one of the things that, you know, basically that's it. I mean, that's, oh, here, when we call it, we define it. You need to create a key. So you're going to need what is called a pseudo-random generator. We'll see how to do that at some point. You need the message, whatever it is, in some text file. You're going to read that text file into memory, and then you're going to give it that message and the key. And then now the key will just gets assigned here. We need to define a function called split that takes the message, breaks it into blocks of size 128, and performs the padding. And then after that, we also need to define the XOR operation, which I can't remember right now. I want to say that XOR is a caret symbol in Python. I don't remember exactly, but we will take a look at it at some point later. A question, let's see. Yes, all of the, so these functions like MD5, SHA-256, all of them use these types of operations of XOR to get the hashes. So this one that I've defined is the simplest one, and the reason, again, what I want you guys to understand, even DES and AES, they will use XOR operations because this is efficient for the computer. Remember that, at the hardware level, computers are just bits, right? 0, 1, 0. And so you can't really have a very cumbersome algorithm, right? So you want to have an algorithm that at the hardware level performs the operation really fast. Does that make sense, guys?
Yeah.
Yeah. And so you will see that the XOR operation is one of the building blocks of a lot of cryptography, especially when we're talking about block ciphers. Okay. Any other questions?
I don't think so.
No? All right. So now keep in mind that, so how can I put this? Yeah, let's see. You have some questions here. So keep in mind, one thing I do want to stress, so XOR, right? XOR, so first of all, you guys understand what I mean when I'm saying that, you have a register or something in memory, and it's just binary, right? So if you have to take this and convert it to a 37 and then you 25 and do an operation, a multiplication or exponent, you realize that the CPU has to do a lot of calculations, right? A lot of calculations. But if it only has to do this, like, an XOR between two places in memory, the computer is very efficient at doing that. And so it means it's really fast, and it can do it really fast. However, I should say, as you guys know, there are also other things, right? So if I do this, what is that one?
I know it, but I don't remember what it's called.
What do you guys think?
And or.
Which one? Well, you said a lot of them. Which one?
Or. Oh, no, and.
And, right? Very good. And. Okay, excellent. That's also like an XOR, right? That's just, same idea. If you can do the XOR as we discussed the other day, and you can do it at the hardware level very fast, you could also do this one, correct? At the same amount of speed? Would you agree that it can be done at the same amount of speed?
Yeah, I don't see why not.
Exactly. What if I do, what is this one? So in this case, what is that one? Or. You could argue, you can see how that's just like XOR is just a bitwise operation. Also could be done really fast, right? And then I could have and then I perform an operation. What is that one? What do you guys think? I made the reverse of them, correct?
Is that one like called not?
A knot.
Or,
Exactly, a knot. The point is, don't get so, as we look at how those algorithms work, you will see that sometimes they can have various things, right? But in particular, that they have fast operations. So we are not necessarily limited to XOR as long as we have equally fast operations like and, not, or, and so on. Make sense?
Yeah.
Yes.
All right, and so that's really the key thing. So almost always, you could think of any XOR algorithm, or sorry, any hash function algorithm, and yours might be very nice and elegant and everything, but if it's slow, and if these operations are secure enough, they're gonna win, because a cryptographic algorithm must always be a combination of two things. Security, of course, but also performance. Imagine breaking, as I said, a movie, right, into blocks and then encrypting each one, and your algorithm is very slow. Your movie will start in an hour. You're not gonna wanna watch that movie, right? Or if it's gonna start next morning. So so imagine if we lived in a world like that, we'd have to adapt. You'd have to, well, I wanna watch a movie tomorrow, so I'm gonna start it today, and then it'll be ready tomorrow. That would be the world. But then some company would make that faster, and so they would dominate. And so you end up with this. So at the end of the day, performance. Now we established, if you look now, one of the things I said before becomes relevant. Where was that? Claude Shannon's conclusion, right? That's why I even highlighted the word in blue. Perfect secrecy. To achieve perfect secrecy, we need this. However, perfect does not necessarily mean we don't always need perfect. Sometimes we just need good enough, secure. Okay? And so that's why you have to, I want you to understand that, why we have the operations, and why you can make some simplifying assumptions about the algorithms themselves. Does that make sense, guys?
Yeah, it's kind of like locking up a bike using a high-class bank safe versus using a padlock type deal.
Yes, exactly. So, Right. So for instance, I could create, you know, I could go get 17 tigers and chain them around your bicycle, right? No one's going to steal it. Also, though, that's going to be very difficult to do. Versus, all right, sometimes, you know, just put a chain, you know, it's $20. Put a couple of chains, put 3 chains. And by the, you know, if you're going in somewhere for just 20 minutes, it'll take people more than 20 minutes to break the 3 chains. They might break 1, but not the 3. And so these are the kind of the, this is how you build the algorithms, right? They're not exactly perfect all the time, although some of them are really elegant, and they prove to be pretty secure. So as you hopefully you can see that, you know, these concepts that we are talking about are the building blocks for all the other algorithms that are complex. Usually we cover DES, and you will see DES how it is. AES just happens to be a little bit more complex to try to implement in code. However, you can do that for your term project, for instance. All right. Are there any questions about any of the things I've said today?
Not at the moment, at least.
All right. So that's the, so hopefully, so going back, that was the algorithm for a simple hash function. You guys will be implementing algorithms like these in the future in some of the labs. In particular, at some point, I have to give you the XOR function. You guys will write the split function. I'll give maybe some hints, but this is something I ask you to do later. The XOR, I just have to give you the operation that you apply for that. All right. You know, one thing I should say is that we're using Python, and I don't know if you know much about Python, but actually Python is an interface to C++. So C++. And if you, as you know, it's C++. C++ is a very low-level programming language. So you're literally manipulating memory. And you have access to operations like XOR and all that are done pretty efficiently. You know, remember that C++ is meant to make applications really fast. So if OpenSSL or a language like that is implemented in C++, right, to be really fast performance-wise and to have access to these operations. So whenever you're doing anything that's bulk, like, you know, of dealing with the message and the cryptography, it's going to be these low-level operations that you can do in C++. And then with Python, you know, Python is an interface, but ultimately the libraries are written in C++. And so you are basically getting that efficiency. Okay? So that's one of the things. All right, so those are the notes for this week. Now let's go to now that I've talked about this, I'm going to motivate the lab a little bit. So let's go ahead and let me download the lab document, which I think it's posted already. So I'm gonna download the document itself. And the PDF. All right, so here's the document. And let me open the PDF as well. All right, so I'm going to share there's two documents here. I'm going to share the screen first with this one. All right, there's going to be two PDFs in the folder. So you guys should be seeing the PDF, correct?
Yeah,
All
the
right.
crypto hash one.
Yeah, the crypto hash one. So you can see here in this lab, we're going to perform these tasks basically. So generating a message digest and MAC. So you're going to follow these instructions, as you can see here. And you're just going to be calculating hash values for different files and then looking at their sizes. You're going to try several hash algorithms such as MD5, SHA-1, SHA-256. All right, and then you're going to just, it's an exploration lab, so you're just going to compare your results similar to last week's. Then you're going to try it with a key. You're going to try playing around with keys of different sizes, see what happens there. Because you could have not used a key. So if you remember the previous algorithm, I added the key as the initial block, temp block, but that could have been a random block. That could have been, you could have written the code in a different way so that we didn't use that. And then one interesting thing is here, you're going to use ghex to take a message, calculate its hash, then run that message through ghex, flip one bit, and then calculate the hash again, compare them, and you're going to present your observations. Okay, so you're going to present your observations there. We're going to skip this part of doing this 3.4, and instead we're just going to look at the Word document that I have here. So I also have a Word document. Let me share that. And in this Word document, you should be seeing it now. I have two problems, okay? So in the first problem, so in the PDF will just show you how to use OpenSSL to calculate hashes, okay? Then after that, I have two problems that I want you to solve. They're different. One is hash related. So let's read through it. Now that you know how to calculate hash values, because you learned it from the PDF, you're going to craft an experiment. Right now, a lot of these labs, you're going to get the best out of it by working with a partner. So find somebody in the class. You can see the list right there. If you want, I can give you guys a couple of minutes to just kind of form, if you don't know someone, find a classmate to work with. Because it's better to understand things if you're sending things to your friends, okay? So I'm gonna want you to craft an experiment. And like I said, a lot of, we're gonna do several labs like this. Craft an experiment where you could send a file to your classmate with the hash value. Your classmate should validate that the integrity of the file has been maintained. You can use email for this task, right? Bonus points will be given if you can also encrypt the file before transmitting. This last step would provide confidentiality. So basically what I'm asking you is, if you only do the hash, you're only achieving integrity because you would send a message in plain text. This assumes that Gmail or whatever you're using, you don't trust the people at Google, and so they would read your message, and you don't want that, right? So what you want also to achieve confidentiality is you would encrypt the message as well. Okay, so then your friend who receives the message, if they want to read it, they have to decrypt it. If they want to check the integrity, they will have to use the tools from the PDF to figure that out. Is that clear for everyone, guys?
Makes sense.
Makes sense. Perfect. All right, glad it's making sense. Okay, now the second problem, this should be a fun problem. This will be your first coding problem. So in the second problem will be a Python coding problem. Okay. So this will be your very first scripting assignment. So what I will do on Thursday is I will, as I said, give you a quick intro of some of the basics of Python. And then after that, I will give you the starter code, right? So I want you to solve this, write your own cipher encryption scheme. So what the objective of this is, first of all, I get to cover substitution cipher in some way. Second, I want you to see that even very insecure algorithms are actually can be somewhat difficult to program, right? So you guys, it's going to take you a little while to solve it. And it's not even, this is not even an encryption algorithm that you should be using anyway. But it's a nice example to start with. So the scheme will be explained by the instructor. So basically the scheme is this. I want you to write a program to illustrate the use of encryption and decryption techniques. In particular, this is referred to as a substitution cipher. You will convert alphabets to numbers and back. So for instance, assume you have an alphabet, and you can make some simplifying assumptions like you only have letters and numbers, right? You're going to need to use the ASCII table for this, right? Hopefully I provided an ASCII table. If not, oh, no, you do have an ASCII table from last week's lab, right? You have an ASCII table there. So you're going to use your ASCII table, and basically you're going to assume that you have an alphabet of 26 letters, where each letter is represented by a number from 26 to 1. In this case, the letter A is 26, the letter B is 25, and so on, okay? So the question is, or what I want you to do is to show that your program is working correctly by encrypting and decrypting a phrase, such as this is ITS 350 at Purdue University. So you have to do that, that encryption, okay? Does that make sense, guys?
Yeah, I think so. I think it'll be even clearer though once we actually start working on
Right,
it.
so on Thursday, I will give you some starter code and I'll describe it again. But the main trick of this is that you have to, it has to be like this. A is 26, B is 25, C is 24. So you can see the numbers are going down, letters are going up. All right. The great thing about this is, you'll see the pattern when you look at the ASCII table. Okay. And there's a quick way, you can just really, if you figure out the pattern, solving this is easy. Right. But you have to solve that pattern. So if you ever program, like when you took your programming classes and you did like the Fibonacci sequence or something like that. So the solution to this kind of revolves around that idea. Okay. So that's going to be your lab for this Thursday. So this Thursday, I will go over this code. You guys will do the PDF problems, the 3 ones, and then you will do this. Okay, so now in the minutes that we have, I'm gonna see who's on this Zoom, I guess. And if you don't know, just find somebody, a partner that you can work with. Okay. Message them or email them or however you want to do it. But just find somebody so that you can do this assignment. Is that clear for everyone?
Yeah.
Yeah.
All right, so I'll give you guys a few minutes to do that.
Do we need to put a our partner's name on our lab report, or should we just mention who it
definitely.
was?
I need to
Okay.
see, because you'll be working with this person probably, you know, usually for the whole rest of the semester, because there's several labs like this. Okay, you know, sometimes we need to do other things like authentication, and I'll ask you to exchange messages with your, as the number of keys becomes more complex. What I want to explain is this: as the number of keys becomes more complex, it's better to have a partner so that you know, okay, I need to have this key from you, and I'm going to give you this key, and you have to think about how to securely exchange the keys. And so working with a partner is really the best way to understand that. All right.
Excuse me, Professor Calix?
Time to work on this. Are there any questions?
Yes, I have one question.
Go ahead, please.
So you said that the corresponding chapter in the textbook for our lab is chapter 22. So if we read chapter 22, then that should make lab 2 much easier to understand, right?
Yeah, lab 2 should be pretty straightforward, right? So you're just gonna do the OpenSSL commands, but yes, it should align really well with the hash lab. Those, if you're talking about the 3 PDF problems, obviously the coding one, I will provide some example of it on Thursday.
And also, Vito, in chapter 21 of the book, I think it was, there is a section on encryption coding in Python. So that might
That's
help.
right. There is something there as well. You're right. Thanks. And that's similar to what we're doing with the substitution, but I will provide a lot more of that. I mean, I will give you the starter code. I'm just not going to give you the pattern. That's the thing that I want you to figure out. Any other questions?
Do you still want us to email you our lab 1 before we turn it in?
You can, if you think that, I mean, it's just a recommendation so that I make sure that you did it correctly. I can give you some feedback, given that it's the first time. You don't have to do that for every lab. I don't. That would be really bad for me. But
So kind of just to make sure we get the format.
yes, I just want to make sure that you've done it correctly before you submit it.
Awesome, thank you.
Usually, as I said, if we were in the lab, I would just go and you know, stand over your shoulder and take a quick look, but I can't do that.
Professor Calix, if I could ask you just one more question.
Good, sure.
So regarding the format of our lab reports, are they supposed to be in a particular format, or is it okay just to take the screenshot of our command and then with a brief 1 or 2 sentence explanation?
Yeah, I really just need to know, you know, this question that I'm addressing. Here are the commands or code that I wrote. Here's the screenshot showing evidence that it worked. And then here are my 2-3 sentences to show that I understand what I'm doing. Make sense? Any other questions, guys?
I don't think so.
Don't get too terrified about, you know, writing the algorithms in Python. As I said, most of the time I will give you starter code. The goal is not about programming per se. It is more about algorithm understanding. I just want you to understand how, you know, it's really, I think after you see some of the algorithms, it'll be clear in your head that, oh, I get it. You know, they all follow this basic idea of this is how they work. Okay, so don't be too stressed. It's not a programming class, right? So we're using Python and algorithms for understanding of how things work versus me expecting you guys to go out and create all kinds of encryption algorithms. All right?
All right,
Okay.
sounds good.
Yeah, great. So if there are no questions, then we're going to stop here for today. And I make sure you've found a partner to work with. You know, get their contact information. So you'll mostly be using email. So we will stop here, and then we'll meet again on Thursday to start working on that other lab and just finish up integrity. Next week, we will start with asymmetric encryption, which I'm sure you will find fascinating because that really brings in a lot of things, a lot of new primitives that we can use to start. Remember, we still haven't gotten to SSL yet. All right, guys. So if there are no questions, we'll stop here for today, and I will see you guys Thursday.
Sounds good. See you Thursday.
Have a good one.
Thank you.